You know, in a perfect world, all the information we'd ever need would be right at our fingertips. Making decisions would be easy. But let's be honest, the real world is messy, it's unpredictable, and it is full of unknowns. And that is the absolute central challenge for artificial intelligence. So how does an AI system find its way through a world where nothing is ever guaranteed? Well, the answer lies in mastering the language of chance, and that language is probability. Let's dive in and explore how AI uses this mathematical framework to see in the dark.
Think about it like this. You've got a flight to catch, and you have to be at the airport by 9 p.m. You look at your app, and you have a few options. Route 1 has a pretty good 95% chance of getting you there on time. Route 2 is even better, a 98% chance. But then there's Route 3. It's a sure thing, 100% certain, but it gets you there at 10 p.m., an hour late. So what do? Well, you instinctively weigh the odds of each route against the cost of being late, which is missing your flight entirely. That very human way of thinking under uncertainty, that's exactly what we need to build into our AI systems.
So here's our game plan for this explainer. We're going to break down exactly how AI uses probability to make sense of this uncertain world. We'll start with why it's so important in the first place, cover the basic concepts, see how AI connects different uncertain events, walk through a really practical example, and finally, take a look at how all these ideas are powering the AI systems that you and I use every single day.
All right, so let's kick things off with the fundamental question. Why can't we just program an AI with a simple, clean set of absolute rules? Why does it need to get into this gray area of probability at all?
Well, the simple reason is that an AI agent almost never has a complete, perfect picture of its environment. Think about a self-driving car. Its camera can get blurred by rain. That's incomplete information. A medical diagnosis system might be missing a key lab result. The world is also dynamic. A pedestrian might just step into the road without warning. And even the most solid rules have exceptions. A toothache doesn't always mean you have a cavity. Probability gives AI a powerful framework to reason and act effectively, even when it's faced with all this built-in uncertainty.
So to handle this uncertainty, we need a formal language. And that language is probability theory. It provides the precise mathematical tools that we need to quantify our beliefs and to make logical guesses based on information that's ambiguous or incomplete. At its very core, probability is just a number between 0 and 1 that tells you how likely something is to happen. A probability of 0 means it's completely impossible, no way it's going to happen. A probability of 1 means it is absolutely certain, a sure thing. And pretty much everything else in the world, from a coin toss to tomorrow's weather, falls somewhere in between.
We actually use this concept all the time without even realizing it. The probability of a fair coin landing on heads is 0.5, right? Because there are two equally likely outcomes. If we roll a standard six-sided die, the chance of getting any one number, like a 6, is just 1 out of 6, and the chance of rolling an odd number, that could be a 1, a 3, or a 5, is 3 out of 6, which is again 0.5. Probability just gives us a precise way to talk about these chances.
In AI, we formalize these uncertain events using something we call random variables. A random variable is basically just a placeholder for an outcome that we don't know yet. For example, a weather variable could turn out to be sunny, rainy, or cloudy. A cavity variable could be true or false. A die roll could be any whole number from 1 to 6. These variables are really the fundamental building blocks for our probabilistic models. Now, for each one of those random variables, we can create what's called a probability distribution. This is basically just a table that lists out the probability for every single possible outcome. So as you can see in this little model for the weather variable, we're saying there's a 60% chance of sun, a 10% chance of rain, and so on. Now, the crucial rule here, the one thing you have to remember, is that the probabilities for all the possible outcomes, they must always add up to exactly 1.
Modeling single events is useful, for sure. But the real power of probabilistic AI comes from understanding the relationships between different events. So let's see how that works.
To do this, we'll use a classic AI example, dental diagnosis. Imagine a patient comes in with a toothache. That toothache is a piece of evidence that we can observe. The potential cause, like whether or not there's a cavity, is the uncertain variable we want to figure out. So the question is, how are these two things, the symptom and the disease, related?
This is where something called a joint probability distribution comes in handy. This table gives us the probability for every possible combination of events. So for example, take a look at that top left cell. The probability of having both a cavity and a toothache at the same time is 0.04, or 4%. The probability of having no cavity and no toothache, which is the most common situation, is way up at 89%. This entire table represents our complete knowledge base for this simple little world.
But what we really want to know isn't just those combined probabilities. We want to know the probability of having a cavity given that we already know the patient has a toothache. This is called conditional probability. The formula might look a little technical, but the idea is actually quite intuitive. What we're doing is narrowing our world down to only those cases where event B, the toothache, has happened. Then, inside that smaller world, we look at what proportion of those cases also have event A, the cavity. So the probability of A given B is just the probability of A and B happening together, divided by the total probability of B ever happening.
Okay, theory is great, but let's make this really concrete. We're going to use that formula and the numbers from our table to solve this patient's diagnostic problem step by step.
So here's our problem. Find the probability of a cavity given a toothache. To solve this, we need two key pieces of information from our joint probability table. First, we need the probability of having both a toothache and a cavity, which, if you remember, is 0.04. Second, we need the total probability of having a toothache for any reason. To get that, we just add up the toothache column in our table. 0.04 for a toothache with a cavity, plus 0.01 for a toothache without one, which gives us a total of 0.05.
Now we just have to apply our formula. We take the joint probability of cavity and toothache, which is 0.04, and we divide it by the overall probability of toothache, which is 0.05. And the result of 0.04 divided by 0.05 is 0.8.
So what does this 0.8 actually mean? Well, this result shows the power of probabilistic reasoning. We started with some vague information and ended up with a precise quantitative belief. An 80% probability gives a diagnostic AI a really solid basis for recommending the next step, like, say, taking an X-ray.
You know, this whole process of updating our beliefs when we see new evidence is so fundamental to AI that it has a special name and a very famous formula that goes with it: Bayes' rule. Bayes' rule is honestly one of the most important concepts in all of AI. It gives us a formal way to go from the probability of an effect given a cause to what we usually want, which is the probability of the cause given the effect. In medicine, for instance, it's a lot easier to gather data on what symptoms a known disease causes. Bayes' rule lets us flip that logic around to figure out the likelihood of the disease given the symptoms a patient has. And the process is actually wonderfully intuitive. You start with what we call a prior belief. That's the general probability of a cavity out in the world. Then you observe some new evidence. The effect: the patient has a toothache. You then use this evidence to update your belief, and you arrive at a posterior probability, which is that new, more informed 80% chance that this specific patient has a cavity. Now, as these AI models get more and more complex, we need some shortcuts to make the math manageable. Conditional independence is a really crucial one. Let's say we already know for a fact that the patient has a cavity. In that case, does finding out they have a toothache tell us anything new about whether an X-ray will also be positive? Not really. They're both just effects of the cause we already know. This is conditional independence. Once you know the cause, the cavity, its effects, the toothache, and the X-ray become independent of each other. And this assumption is a super powerful tool that makes the math for complex AI models a lot simpler. So we've covered a lot of theory here, from basic probability all the way up to Bayes' rule. Now let's bring it all together and see where this powerful toolkit is actually being put to work out there in the real world.
And the applications are literally everywhere. Medical systems use these exact principles to suggest diagnoses based on symptoms. Self-driving cars are constantly calculating the probability of what other cars and pedestrians are going to do next. When Netflix or Amazon recommend something to you, they're calculating the probability that you'll like it. Spam filters, fraud detection, even language translation, they all depend on probabilistic models to make smart decisions when things aren't 100% clear.
And all of this brings us to a final, really crucial question. Probability allows AI to act rationally without being totally certain. But as these systems start taking on more and more responsibility in medicine and finance and transportation, we have to ask ourselves what level of confidence is acceptable. Is 98% certainty enough to trust a car with our lives? Is 80% enough for a medical diagnosis? This isn't just a technical question anymore. It's a social one, and it's something we're all going to need to think about as these incredible systems become a bigger and bigger part of our world.